but it actually is cheap for what you get. Only $10 billion to get the world's best scientific machine ever built. So this is the Large Hadron Collider. The reason it's in a, well, no, we'll talk about why it's in a tunnel in a little while. All right, so here's some questions I want to ask about this machine and what we're learning in a little more detail, not just those three basic questions. Why is this thing so big? Why is it 17 miles around? Why do the protons go so fast? Is this thing safe? There were some news reports that maybe it wasn't safe. We'll talk about that. How do you accelerate protons? What things have we learned from this? How do you see such small particles? And we've kind of talked about that with Rutherford's experiment. You really see what the particles, how they affect other things. What do we expect to learn? And, last of all, does this affect me? Why should I care what's going on in the other side of the world where physicists are smashing particles together? All right. Any questions so far? Comments? Bored yet? Yeah?
I've been to CERN.
You've been to CERN. Cool. When'd you go?
I lived in everybody knew me.
Right. Not me, so not everybody, right?
I lived in Germany last year. And
Okay.
we went, most of the AP classes.
Very nice.
The Canadians and I was in the national school. And the Canadians and the AP classes and the anatomy class got to.
So did you actually take a tour? I've never done that. Did you get to go in the tunnel?
I don't.
They don't? Well, no, because it was operating. When you're operating it, you can't go in the tunnels because it's dangerous, yeah. But cool.
It was interesting.
So what was your favorite part?
I don't know.
Well, huge impression it made on you, right? It's a cool place.
Yeah, I'd like to go again.
Yeah. I always bring T-shirts that say CERN for my kids home, or something like that. All right. So let's ask some of these questions. Why is this thing so big? All right. And I want to look at a racetrack. Suppose these cars are going really fast. What happens as the cars go faster to the size of the racetrack? You got to make it bigger, right? The faster a car is going, the harder it is to turn it. So if you want to go really fast, you need a big racetrack, a big, long, wide racetrack. And that's what's going on with these particles. The more energy we give them, the harder it is to turn them. And so we have to keep making these machines bigger and bigger and bigger. And the reason it's 17 miles around is that's the smallest one we can make and have the particles going as fast as much energy as they have. And so, just like in a race, if you don't, here's a place where the car was going too fast and smashed into the wall. So you have to have a very, not a very quick turn if you want to go fast. And so that's why it's so big, actually. It's a pretty simple reason. This is some math. We won't worry about that. All right. So why do we care that they go so fast? Well, we want a lot of energy to do two things, really three things. The first one is we want to try to break things into smaller pieces. So if you smash a car against a wall, the more energy it has, the smaller the pieces that will come out. So suppose you wanted to know what your car's made of, or your parents' car, Suppose you want to know what your parents' car is made of and you don't have any tools to take it apart. What can you do? Well, you get it going really fast and you smash it against a brick wall. Don't tell your parents I told you to do that, all right? And when you smash it against a brick wall, all the pieces come flying out. The carburetor and the tires and blah, blah, blah. So you know what the car is made of because you broke it up into smaller pieces. And the faster it's going, the smaller the pieces are that come out. So the more energy we can get, that's why we want these guys to go so fast, the more energy we can get, the smaller distances we can probe. That's one thing. But also, we want to get things that are really hot. Hot's maybe not the best word, but the universe, when it started, was really hot. And so if we want to understand the origin of the universe, we have to try, we actually try to recreate those conditions from the origin of the universe in our lab. And so we want things really hot, like the universe was. And the faster the particles go, the more energy, the hotter it is when they collide. So, cars give a good example of what we're doing. And in fact, this is why this field of science has two names. One is called elementary particle physics, because, elementary means the fundamental particles. We're trying to study the fundamental particles. But we also call it high energy physics, because we use very high energies of things that collide to try to understand the structure of matter. And so 24 hours a day, 365 days a year, well, not quite, but mostly, we have protons in that machine going the speed of light, smashing into other protons. and they hit each other every 25 nanoseconds. 25 times 10 to the minus 9 seconds, these particles collide. And I'll show you what happens when they collide. Right? So there's another reason why the particles go fast. Anybody ever seen or heard of this equation? E equals mc squared, right? So what does E mean? And what does M mean? Mass. And what does C mean? Speed of light. But we don't have to worry about C. That's just a number. Let's look at the equation like this. Energy equals mass. So if I take, I don't want to drop this. If I take something like, this piece of chocolate, and I hold it right here, it's got what we call potential energy. And if I drop it, it speeds up. And that potential energy changes to what we call what? Anybody know? Kinetic energy, right? So potential energy is one kind of energy. Kinetic energy is another kind of energy. And mass is actually just another kind of energy. So same way I can change potential energy to kinetic energy, I can change kinetic energy to mass. So if the protons have a lot of kinetic energy when they collide, I can actually create mass. And so by this thing. So energy of motion, kinetic energy, can be changed into new particles with mass. And the more kinetic energy, the more massive the new particles can be. Now in chemistry class, your chemistry teacher will tell you you cannot create or destroy mass. But the chemistry teacher is really lying to you. Because kind of in chemistry, you can't create or destroy mass. But in physics, we create and destroy mass all the time. Because it's just another kind of energy. And if I can change potential to kinetic, then I can change kinetic to mass. And we create mass all the time. It's as common as brushing your teeth or something. In fact, it's more common than that. Because we do it every 25 nanoseconds. We create new mass from the energy of the motion. So this is kind of an important principle for us. If I want to create a particle with lots of mass, which I like to do, I like to have a lot of energy to start with. And that's why these guys go so fast. All right? So let's see. All right. So, well, how high is this collision energy? We're talking about high energy physics. Well, it's really not a lot. It's about the same as the energy of being hit by a piece of paper. So you might think, well, that's not very high energy. If somebody hits you with a piece of paper, it doesn't really hurt that much. But you got to remember that a piece of paper has a whole lot of particles in it. So if instead of a bunch of particles hitting you, you had one particle hitting you with the same amount of energy, it would really hurt. Right? So it's like saying, if you have something really that's big but doesn't have a lot of mass, like a piece of styrofoam, it doesn't hurt you much. But if you have something small with a lot of mass, like a BB, it would hurt you when it hits you. And so even though the energy in a macroscopic scale is not a lot, in a microscopic scale it's huge. It's the more energy than we've seen since shortly after the universe was born. At least the energy density. The amount of energy in a small point is greater than we basically see ever. And so it's a lot of energy per particle, even though in some sense it's not a lot of energy. But there are lots and lots and lots of particles. So if you were to stand and let the beam, we have a beam of particles going through the machine, if you were to actually have that hit you, it would kill you because there's lots and lots of particles, even though any single particle doesn't have lots of energy. All right. That's cool. All right, so is this thing safe? When this was first turned on in 2010, there were lots of reports in the news that it might not be safe. One of the reasons is because inside the tunnel while it's running, it's not safe. Here's somebody in the tunnel, but it's not running. He's riding his bike. But while this is running, it's not safe. In fact, while the machine is running, the tunnel is full of radiation. And when you turn the machine off, the radiation's gone, and you can go in the tunnel. So all of you have something in your house just like this. If you turn it on, inside it's not safe because there's a lot of radiation, and when you turn it off, it's completely safe. What is it? Your microwave, right? And so this is just like a microwave oven. Right? Yeah.
Is the radiation synchrotron radiation from the acceleration of the particle?
Primarily. Yep. Yep. So that's why when you turn it off, it's gone. Okay? And so, and so what we do is we make sure before we turn it on, of course, that there's nobody in the tunnel, because that would not be good. It's like, don't get in your microwave before you turn it on. That would not be good. All right? So don't get in the tunnel before you turn it on. But as long as that's the case, it's perfectly safe.